Hello, my name is Matteo Gianollo. I am a PhD student in electronics at Politecnico di Milano. Today, I would like to present you the challenges and implementation of a miniaturized quadruple mass gyroscope. I would like to start the presentation with a question, which is why should we design and implement a high-end miniaturized MEMS gyroscope? The answer is the evolution of the consumer inertial sensor market towards the so-called consumer plus market, whose feature includes the compatibility with the consumer product die size, together with implementation using a mass market process. On the other side, it requires an angle random walk performance below 10 mdps over square root hertz, and both offset and scale factor stability for a navigation application, but also a vibration robust design. With all those features, the enabled applications are augmented or virtual reality, and also short time navigation, which can last from a few minutes to a few tens minutes. The presentation is divided into sections, device design and experimental results. So let's start with the first one, which was carried out with the FEM analysis using COMSOL multiphysics software. So to achieve consumer plus market requirements, mechanical structures which are symmetric along the two axes are widely used. Those can be divided in two main categories, which are continuous resonators, like bulk acoustic waves or DRGs, or lamped devices, like quad mass structures, which we have chosen because they exploit a larger modal mass, larger angular gain, and a large drive displacement, together with improved mode decoupling. We will operate our quadruple mass gyroscope in Lissajous frequency modulation mode. In literature, typically available mechanical design, which meet the high-end performances required by consumer plus market, like the one here shown, proposed by Schell and other. They do not meet the area constraints of the consumer product die size. So we had to shrink down the dimension of our quad mass gyroscope to 1.1 times 1.1 millimeters squared. Here in the table, we reported the main process constraint we had to cope with during the design, like the design area, which is only 2.6 times 1.2 millimeters squared, and the process thickness of 24 micron, alongside a picture of the layout of our miniaturized quadruple mass gyroscope. Here we reported the eigen frequency simulation of the first two modes along the x-axis and y-axis of our gyroscope, which are placed in frequency at around 50 kHz, with a mode split set nominally to 80 Hz to cope, to guarantee an adequate sensing bandwidth for consumer plus applications. In the picture, we can appreciate the role of the outer lever in coupling the motion of the four masses, but also the role of the tuning fork in forcing the anti-phase motion. The modal characterization was performed on several devices for two different values of motion amplitude. Both frequencies and quality factor lie in the expected range. However, as can be seen in the picture, in the plot with the dashed line, a hardening nonlinearity becomes visible when the target motion of 5 micrometers is approached. In such a small area, it is difficult to perfectly decouple the two modes. Indeed, a y-axis displacement causes an in-plane rigid rotation of the x-driving shuttles, which itself causes a x-y displacement of their tips, and therefore a gap variation between the shuttle comps and the fixed ones. The effect of this spurious coupling is a tone at double the cyclic frequency. So during the design phase, we have worked in order to minimize this unwanted and undesired coupling, acting on the position of the spring connecting the proof mass to the shuttles in order to reduce the torque arm, but also on the springs connecting the outer lever to the shuttles and the springs connecting the tuning fork to the shuttle itself, in order to rebalance the inner and outer constraints. The second part of this presentation, I will show the experimental results carried out in the laboratory. So in order to read an input angular rate from the sensor, we have to make the MEMS oscillate. So we have to design a primary oscillatory loop around the MEMS for each axis. Each axis of the MEMS can be modeled by its RLC equivalent circuit. The primary loop front-end stage is based on a charge amplifier topology, which reads the motional current coming out from the sensor. Its output goes to a 90-degree analog phase shifter, which is needed to satisfy the Barkhausen criteria on the phase. Then we have an hard limiter stage, which is used to speed up the startup phase and to meet the Barkhausen condition on the gain. Finally, the loop is closed by an H bridge, whose supply is regulated by the secondary loop, which is an AGC loop. That is needed to control the motion of the proof mass of the sensor. Finally, the output of the front end goes through the digital signal processing chain, mainly composed by a frequency to digital converter, an amplitude demodulator, and low pass filtering. So in the figure, we reported the frequency spectrum measured at the output of the front end. We can appreciate a tone at the split frequency, which is the signal tone. But we can also see a spurious tone at double that frequency caused by the undesired coupling between the modes. The noise floor lies at 20 microhertz over square root hertz at the signal frequency, which corresponds to 6 mdps over square root hertz per combined output from the two axes. So finally, the first system operation was demonstrated with an input sinusoidal angular rate at 2.4 hertz with 250 dps peak amplitude. Here we reported a sample captured at the output of each single axis, the dashed blue and red lines in the plot, and a combination of the two. So in conclusion, we have here presented a miniaturized quadruple mass MEMS gyroscope with an active area of only 1.1 times 1.1 millimeter squared and an angular random walk performance of only 6 mdps over square root hertz. The major challenges faced during the design phase are the mode decoupling and the associated second order harmonic generation, the limited angular gain, and the hardening nonlinearity, and of course their impact on the electronics development. Future research includes coupling the sensor, the pod mass gyroscope, to a fully integrated circuit with internal reference extraction and digital processing, but also characterization in terms of stability, temperature stability, full-scale range, and linearity. By the way, the electronic system is much more complex than the one here presented, and so for more details, please attend the oral session C1L04, which will be held tomorrow. This is all from me. Thank you very much for your attention, and I will be glad to answer all your questions.